Right. So please go ahead. Thank
Okay,
you.
thank you very much again for the nice introduction and the invitation to this seminar series. Today I start with Ferroelectronics or Ferroelectrix, from memory to computing. I think this will also be a continuing topic, as you already mentioned that Michael Nimier will also will give a talk in like the two series again, and as we have a lot of collaborations in this field in the past. So I try to start with a very general slide on why do we go from new devices to even computing. This is because of maybe very known to everyone in this field who's doing memory-centric computing or in-memory computing, but still give you a quick reminder. So the AI hardware requirements are drastically increasing over the years. This might be a bit old, but in the end, this is still valid data. So we still see an increase in the required operations of AI operations, neural networks, CNNs, and so here in this case, mainly convolutional neural networks over the years for various tasks like computer vision, as well as transformers. I would say in the last years or last months, this increase was even steeper. So typically, we now have like a double of the compute performance as the number of operations or the number of parameters every 2 to 3 months. Probably we already see a bit of a saturation, especially because of these the limitations. I will come to this. So because typical hardware which shall support that is not meeting these exponentially growing requirements for AI. There are various things, the slowdown of Moore's law, which we already have seen, you could say the last 20 years in a sense, by following the number of transistors per square, but not necessarily the performance density. Furthermore, due to the very large memory requirements, a slowdown in the energy efficiency you can get with external DRAM. You get more DRAM, you get a higher density of them, but calling the bit, so the energy efficiency of the memory is still not scaling that well anymore. And all that combines the in the community very famous von Neumann bottleneck when you separate memory and CPU. So the additional energy which is required to call the memory into the algorithmic logic unit, where you almost don't use it because you have only a very limited number of operations you do with it. The actual bandwidth requirement limitation for this data bus and the very limited number of operations in the CPU as well. So all of that we try to tackle if we go to brain-inspired computing. So we definitely see an increase in the compute efficiency with the CMOS technology nodes, no doubt. But if you look into that, you already see a kind of a slowdown over the technology nodes. And we are still far away from the compute efficiency we would need to have when we have a brain computing, so both in performance, so TOPS, but also in the compute efficiency, TOPS per watt. So still the brain with like 20 watts is heavily out competing every CMOS-based technology. So and the various accelerators using those technology do not significantly outperform the compute efficiency. So one way to go for this is analog and in-memory computing. So there we try to break the typical von Neumann architecture to improve both performance and energy efficiency by getting the systems closer to the memory, so reducing the von Neumann bottleneck. So that's what we call near memory computing, where we try to place the memory even on chip, and so don't have it separated in different systems. And you could also go even one step further with in-memory computing, where this you, instead of transferring all the data from a external memory towards your processing unit, be it a GPU or a CPU, you directly compute inside that memory, and you use the memory architecture to do these operations. For example, XNOR AND operation, which you need for multiply accumulate. So, and you can also then use this same in-memory computing architecture to build neuromorphic systems. So you can use the in-memory computing as the synaptic fabric and combine it with maybe also digital neurons to run neuromorphic systems. Okay, so such neuromorphic computing accelerators or in-memory computing accelerators we are currently developing. That is clearly a multi-hierarchically level venture. And I will start with the memory and will go all the way up to these memory macros, which are then computing. So we call it compute macros here, to architectures and optimized algorithms for such hardware. Okay, to the memory devices. So in principle, for in-memory computing, you could think about a lot of memory cells which can be used, both volatile and non-volatile memories. Here I showed you the non-volatile memories. The basic advantage of using non-volatile memories is that you can switch off the complete system, you complete in-memory computing ASIC without losing the memory. If you have a volatile system, you have to somehow store the data somewhere else. So there are a lot of reports on SRAM-based in-memory computing. Those would, on the system level, always require the storage of the weights and so on outside in another system, and the booting at the the boot process. As these memory or the neural networks getting larger and larger, this boot process also is a bit delayed. So here we use non-volatile memories, so we can keep the weights in these convolutional neural networks, so the kernels, in the ASIC. And we have various possibilities. So we have the memories like eFlash, which are very standard in the industry. They are useful until CMOS nodes like 40 nanometer. Below, it's getting extremely hard to integrate them. So you cannot integrate them in CMOS nodes below, or very hard, maybe 28 nanometer, you will still see some realizations. Then, because of that, a lot of other emerging memories have been investigated, like STT-MRAM, phase change memory, PCM, resistive RAM, and ferroelectric types like FERAM and FeFET. So all of these memories are emerging memories because of the slowdown of the embedded flash scaling. So STT-MRAM is a very mature memory, but has a very, very low on-off ratio, which makes it very hard to do in-memory computing. It is possible, Samsung has shown that it is in principle possible, but the required periphery overhead is very high, and the cell density due to this is also not high. Also, RAM has been shown a lot, and phase change memory have been investigated. We, in particular, use the ferroelectric field effect transistor because it's quite similar to eFlash in the sense that you have a storage transistor, which has a very high on-off ratio. similar to SRAM, Flash, and FeFET. All of those have a very high on-off ratio, which makes it very easy to do in-memory computing. There are a lot of write-based advantages of FeFET. However, they are not too critical for in-memory computing if we stay in a weight stationary case, which means we program the weights once in the in-memory computing system and then keep it for very long. So that's not too relevant. The write endurance of FeFET is not as great as for the other emerging memories. However, that is good enough because we assume a quite weight stationary case. Okay, so what is a FeFET actually? This might not be the most known device in general. So what is, from a memory perspective, known quite well is the ferroelectric random access memory, which uses an MFM capacitor. There you implement a ferroelectric material between two electrodes. And this ferroelectric material has a special state where the dielectric dipoles are aligned to each other spontaneously. Physically speaking, there is a spontaneous polarization. So that means you have a charge, a ferroelectric charge, independent of an applied external field, like in a dielectric material. And it's possible by applying voltage pulses to switch these dipole in this material. Having these dipoles aligned to each other in the same direction makes it possible to induce a external stray field around it. So when you use this stray field in the stack of a field effect transistor, you create a ferroelectric field effect transistor. So having this ferroelectric material in the gate stack will result in a additional field in the channel of the material, and dependent on the orientation of these internal dipoles, you get an additional shift in the transfer curve of such a transistor. If you shift the threshold voltage of such a MOSFET, as you all know, to the left, then we call this a program. And if we call this, shift this to higher threshold voltages, we call this an erase. And if we read out this transistor, now we have the case that the current in the program is orders of magnitude higher than in the erase weight. So because this is actually a logarithmic curve. So because here in this range, we have the famous Boltzmann constant of 60 millivolt per decade. Typically, so in the field effect transistors we are close to this Boltzmann limit. Okay, but there are also other implementations for ferroelectric based transistors. So you could also include this ferroelectric material in the so-called back end of line. So having the ferroelectric in the back end of line, like most of the other resistive memories, like RM and FRAM. Now with new materials like hafnium oxide, it's also possible to implement that in advanced nodes. So that's what we call SEMFET. This has the advantage that you have a separated ferroelectric capacitor and MOSFET. So they are disentangled, so you don't have to develop those together with the other MOSFETs. What is a bit of a challenge is that you have to optimize the capacitor divider, but you are flexible on this. You can also include these ferroelectric materials in thin film devices. That's very interesting because you can do 3D integration. So several groups have shown it for different channel materials already. And one interesting prospect is that it can also be implemented in flexible substrates in this case. So it could be used for neuromorphic computing in variables or other configurations. And a FeFET can be also integrated not just in the bulk transistors, but in all advanced node configurations in general. One has to consider that the ferroelectric material is quite thick to be crystalline and ferroelectric. So this is a limiting factor in more advanced nodes, but what was already shown in FDSOI technology, which is a bit more scaled and has the interesting advantage of having a front and a rear gate, which makes it possible for other architectures of realizing the memory. And for example, by reading out on the rear gate. Okay, so good. A very, very basic graph here for deep learning. So one neural network and the operation which we typically have to perform in those, also the same in transformers, basically. Most of these operations are multiply accumulate operations. So weighted sum operation where we have a certain weight, which is the state of the memory, for example, the FeFET, and a certain input, and the application of a certain bias, and then the subsequent operation over all these nodes. So that's the main reason why we try to investigate this, because this weighted sum operation is very easily implementable in any memory array. For the case of FeFET, we also still have to think about how it can be implemented specifically. So when we have a FeFET, then this has a very high on-off ratio, as I said, which makes it somewhat easy to read out. But if you try to accumulate it, then you will see that because it is a transistor, it also has a certain VT variation, and this results in a very high current variation. If you want to follow Kirchhoff's law and accumulate the current, and so you stay in a current mode, then it will be very difficult to read it out. So that's why one configuration we checked was the one FeFET 1R configuration with a resistor which has a high or actually a low mismatch, so a low device-to-device variation. And so this makes it very easy to accumulate the results. If the weight is a 1, so here we have a low VT. If the weight is 0, we have a high VT, so there's no current. So we can accumulate easily the multiply operation, which is here a binary multiply operation, and then accumulate this current over the drain line or source line, no matter what. Here you see such statistics of the results for a smaller amount of accumulations, but this can also be done at much higher numbers. So that's then used, this concept of having the ability to accumulate the current is then used in memory arrays or compute macros. One part of that was using current mode analog digital converters. So if this current is then accumulated on the drain line, we would like to digitalize it very accurately. And as it's always a debate in the in-memory computing community, what is the power consumption of the ADC? So you need to have an ADC which has a very, very high energy efficiency. So you only talk about some femtojoule per conversion. And that's what we implemented here in such a current mode ADC concept. We also developed further ADC concepts like single slope ADC, which shows similar energy efficiency and can be implemented in the current mode. Furthermore, it's possible to stay in the voltage mode when we do a charge domain computing. However, I will not have the time to discuss this today. This might be an approach which is also very energy efficient. we have developed segments due to the fact that having this resistor or this resistive element has a significant influence on the area efficiency. So we want to have a very high density memory array. So we develop segments of these FeFETs and only couple it with one low mismatch resistive element. The main reason for this is that in deep neural networks, we only use parts of these kernels per layer or sequentially. So there's no need to be able to address the entire array at a certain time. Some researchers are like cascading the neural network over the various macros. Each of the macro has a very high energy efficiency, but if per time, so tops per watt per and top per second. But if you look into then the energy efficiency over time, this is in the real workload, this is actually limited. Here we try to have a very high utilization. We just always use the same periphery for the entire network, and so get a high utilization of the peripheral IPs, only addressing always the specific FeFET at the time. So with this, we create the processing element, which requires the word line drivers. So the word lines here are always the input. So we have an input buffer and max this different results in this various segments into the analog digital converter. As this has not the full precision which we need, for example, 4-bit or 8-bit individual operation, we also implement shift and add operations to get the full precision. So we combine different, either different time cycles or different ADC outputs. Here we can see such a crossbar layout, which we created in the 28 nanometer process, 28 SLPE of GlobalFoundries, including all the digital interface, the SPI interface, scan chain, and so on. So this is the compute macro in this scenario. Or the processing element. Now, how can you build a bigger accelerator out of that? So as I said, we do bitwise operations. So how can we actually map all these bitwise multiply accumulate operations into our system? So here you can see this weight mapping process. We have all the input features to the macro, and we store these kernels in the array. So and what kind of operations do we have to run? So we have to basically do a lot of those multiply accumulate operations and sum them up over all bit precisions and weights. And that looks like then as given in this slide here, we place the different precision, the different bit significances in the different segments of the different kernels, of the different elements of the kernel, and of the different kernels. And so we distribute all these bit significances and kernels over the processing elements as well as over processing element clusters, as typical crossbars are limited in the like megabit range. And so if you have larger networks, you require larger number of such processing elements, and to be still bit precise and distribute the workload, you have to compile the correct operations over the processing element cluster and in principle also such tiles. We have been able to, or are working on creating such accelerators with these processing element clusters, which are attached to RISC-V cores and use hereby ARM memory compilers for the implementation. So this is how we implemented in this 28 SLPE technology. The RISC-V core in our case is the EMSA5 core. So this is a special core which was developed at Fraunhofer IPMS to be compliant with requirements of functional safety. And these are then used also for this in memory computing. And we develop also the software on this RISC-V to control the accelerator with GCC. In general, such architecture has then or supports various interfaces, so we can read out various sensor types like with QSPI, UART, JTAG, and even have a Gigabit Ethernet connection available so that we can be very fast and have a very low latency communication with the external sensors and maybe demo displays. So we developed the software stack, so that's gives us an end-to-end architecture. So a system C model was developed for the architecture optimization, and we have developed an FPGA dashboard for that. In principle, this concept of in-memory computing based on a resistive approach. So we use really accumulated currents for sure significantly improves the MAC energy efficiency. This is mainly dependent then on the required current. So that means the higher the bit weight is and the higher the input precision, the lower the energy efficiency. So the more we go towards one bit operations, binary neural networks, the higher the energy efficiency, and then we can go like to 10,000 TOPS per watt. However, if we want to operate it with like a 4-bit weight and a 4-bit input precision, then we are already dropping to like 1,000 TOPS per watt. But that's still a good value for most scenarios. So 4-bit weight and 4-bit input precision is a typical value where you still can have very well performing CNNs. But this is only the reality if you look into those macros. If the overhead, which I just showed you, the digital overhead on system level has an influence, so that results in currently a drop in the whole system efficiency of this concept, which we call Felix, so that for a 4-bit weight and a 4-bit input precision, we are a bit below 100 TOPS per watt on a system level, which is still significantly better than any GPU realization right now. And as you can see, most of the power consumption is still allocated in the digital blocks. So the more you go towards an analog computing implementation, you could reduce this power consumption, but it's always a balance between dedicated hardware and a bit of a flexibility on the support neural networks and so on. So there is always this drawback. The more you are able to develop a hardware very precise to one specific neural network, to one application, it would be possible to even further improve the energy efficiency here, because we could reduce the required overhead in the digital control system. As which you know, like deep learning, convolutional networks, with such in-memory computing systems, you can also run a lot of other test cases. So for example, it's possible to support memory-augmented neural networks. They are needed for data training or to support training. So typically CNNs are trained with a large number of training data, and they are then giving you a predicted class trained with all these very large training data. You have a test data, you have a training data set. But in reality, in most application scenarios, it is not easy to have all this training data. So you actually have a very limited amount of training data. For example, consider failure cases. Because as you have a very limited number of failure cases, it's difficult to train those. With memory-augmented neural networks and content-based addressing, it's possible to characterize those new images based on a memory-augmented neural network, where you extract the features in these networks, and then you store the additional features. So this is done in this way. You have a certain feature extraction network. This extracts you the features of such images, which you can see here. And then you compare those features with all the stored feature cases in a hyperdimensional space. And here, for example, these quantized features are compared with all the stored data, which is then called a so-called associative memory, because it's associating the input with the stored data. And where you have a match, you have the, for example, highest or lowest current, and then you can say, okay, this image has the most close features with a pre-recorded image like that. So, and by that, it's possible to create new training data for later optimization of the neural network in general. And and these memory-augmented neural networks are possible with a 2 FeFET cell. So you have 2 such FeFETs, and the input is connected in the sense that what we have seen before, the word line and the word line of the second are actually digitally inverted inputs, and we collect all these the currents on a match line. And here you see all these match line currents are then sensed, and the ones where you have the lowest current is, for example, the match. You can also do other operations like comparing. You again use the same cell, 2 FeFETs, so a search line bar, you have a match line. If the VT, which is stored in this FeFET, and maybe now I have to mention that it's not only possible to have 2 VT states, but you can also have various VT states stored in this FeFET. The actual VT state can be interpreted here as a certain value like theta. And now you can compare if the input, so the voltage to the source line, is smaller than this value theta, because then you have no current. If it's higher, then you have current, and vice versa. You can also store other values. So by that, you basically can compare the input to the stored value. So in this scenario, we always fix it to HVT 1, and when we flip it, so the HVT is on the left, then we can run the operation larger than. If the HVT is on the right, we can run the operation smaller than. And such maybe trivial comparison can be then used when you want to create decision trees, also a very conventional AI or machine learning operation. You use these to create various branches of such a decision tree. Each such decision tree has a certain comparison operation, smaller or bigger than theta, for example. So you compare, is it smaller or bigger, then go in this branch. You compare again, is it smaller or bigger, then you go into this branch or this branch. And the same we do here in these match lines. So is there current generated by this cell in this match line, yes or no? Is there current created by this match line, yes or no? And you use then the match lines which have, or you use the match line which has the lowest current. That is then the branch in the decision tree which is selected in this operation with the inputs x1 and x2. Which we apply to the source line and source line bars. And in principle, to go even higher, one can create such deep random forests, which use a lot of such decision trees. Your decision trees can be mapped into forests, and you can even have such a leveled structure where you then always use also the concatenate input per layer. These deep random forests incorporate the core features of the deep learning model, very similar, but they are very much less famous than like deep neural networks or convolutional neural networks, but still achieve quite good accuracy, which you can see here, for example, for test cases like EMG, so electromotography, so of the movement of your hand. And for those time series data analysis, typically long short-term memory, LSTM, is considered a good approach. However, it's also limited. And with deep random forests, you can significantly outperform LSTMs. Now, all these networks acquire that you have a high bit precision. And as I said so far, we can only store a 0 and a 1 in the FeFET, but actually we can have several VTs. When we say we can have a bit precision of 3, which means we can store 8 VTs, then it's possible with without any multiplexing operation to achieve almost the software baseline accuracy. So when we would have 4 bits being stored in the FeFET, we would reach already the software baseline. As I said, typically for 4-bit operations, you almost always reach significant accuracy limits. And with this, still even with 3-bit, you're outperforming software level LSTM for this data case. You can also use this very same architecture for a completely different computing approach, which is hyperdimensional computing. So again, we would use those 2 FeFETs, having a source line bar and a match line connecting to them. Depending on which states, so here you can again see that we can store different VTs in the FeFET. When we combine this with the drain line and how this actually looks like, we can get these kind of current over voltage curves. And you can see that there are always these kind of minimum values. That means these minimum values are always the match. So this what cam cell is then matched to the input. But it's not only matched, but you can also use these cells to have a distance. So as this curve here is quite proportional to this, we can also create distance functions. So, and that makes it very interesting. So we can have up to a 3-bit precision distance per Kämfe cell. So, and then we accumulated the distance. We can store, and for hyperdimensional computing, we can store these hypervectors in exactly the same arrays as we discussed before, with the similar bit precision like 2-bit or 3-bit, and can run the similar operations. This is a result which was in collaboration with Michael Nemier, and he will also, I assume, present a bit more and in more detail the results of this computation. So here you can see the results of this, that at 3-bit operation of the, or a 3-bit memory operation of the FeFET, you have almost no reduction in the software level accuracy for hyperdimensional computing. This is one test case, which is the IRIS database. And you can see that we significantly reduce the energy when compared to a GPU, as expected, but also to a typical other hardware which is investigated for hyperdimensional computing. When talking about the FeFET, now I said typically that for associative memory or content addressable memory, it requires to use 2 FeFETs, but we have also shown that it's possible to use a single FeFET, so it's possible to reduce the area or improve the density when we just use a single FeFET. That's simply done by time multiplexing the result. So in this similar case that we have a FeFET and a resistor, it's possible to run these 2 steps, where in the first surge step, we have only the mismatch current when we apply a 1, so a high voltage, to a 0 state. So here, this is this case, a 1 on a 0 gives you a high current. So this is mismatch current. And in the second step, we only see the 0-1 mismatch. So we have a 0, which is then actually a higher voltage. So between these 2 steps, we switch the surge voltage level 0 to basically the same value as the one before, and the 1 to even a higher. So actually, in the hardware, we have 3 read voltage cases, so already ternary, and switch between step 1 and step 2. And by this, it's possible to, in the first step, see all the mismatches of 0, 1, and then of 1, 0 in the second step. And by combining those, it's possible to have, again, the whole match cases, actually. So if we use all the matches minus the mismatches in these 2 cases, it's possible to get the complete matches, and so the distance between the minimum match and all the different match lines. Here you can see this. So the match line currents are proportional to the distance in both states. Good. I already introduced to you that it's possible to have not just this FeFET, which we investigated in the 28 nanometer CMOS technology of GlobalFoundries, but it's also possible to have ferroelectric metal field effect transistors, which we call FEMFET. There, the ferroelectric material is connected to the gate of the MOSFET, but separated. Quite similar to the ferroelectric random access memory. In the ferroelectric random access memory, the ferroelectric capacitor would be connected to the drain terminal. So this scenario is exactly the same as a FeFET, but with a separated ferroelectric capacitor and the MOSCAP. We have been demonstrating this concept in a 180 nanometer technology, where we integrated the ferroelectric cap in such XFAB-based high voltage SOI technology. We used a similar array concept as shown before. And we have been able to see that there is a significant memory window between the high VT and the low VT states. As you can see, the program pulse width here can also go down to like 10 nanoseconds, still having a separation between the high VT and low VT states. So typically what we would work with is obviously like 100 nanoseconds. That's a typical value for FeFET, and this is also working for the FEMFET case. We have a significantly improved endurance cycle for the FEMFET in comparison to the FeFET. This is interesting when you have to use much more updates. The result or the reason for this is that now we have a symmetric ferroelectric capacitance, whereas in the case of the original FeFET, we have a MFIS state, so this stack, which is not symmetric and gives more influences of reliability concerns. And so in the case of FeFET, you have an destruction of the interface layer over these cycles, where all the generation of the charges, they deteriorate the interface layer. Whereas in the case of this metal ferroelectric metal stack, you have a very symmetric stack, and so the endurance is significantly improved. We have already demonstrated such endurances significantly improving 10 to 8 to 10 to 10 cycles. Also, other researchers focusing on EFRAM have shown that for such a scenario, the endurance can go up to like 10 to 12 cycles. So almost getting into unlimited endurance scenario. Also, the retention of this is good enough. However, we have a significant trend in the VT over time for this. So one has to consider. Good. So now I showed you all these architectures and implementations. I also showed you various realizations apart from the standard convolutional neural networks. Now I come back to the optimization of these algorithms, which we use for CNN accelerators. So typical, if you want to have an end-to-end CNN operation, you have to really look into the entire neural network. And here I am discussing the Felix architecture and how this is looking like for some reference cases, like the ResNet 20. So residual net 20 has a certain number of layers, and each convolutional layer has a certain output size, which we show here. So we have convolutional layers, we have max pooling layers, average poolings, or fully connected layers. And all of these layers have a certain kernels, which we have to map into the hardware. And that results in a certain number of MEC operations, which we have to run. Typically, because of our segment architecture, which we achieve a very high utilization. But in the first layer, where we have a very high number of the individual max per, or very low number of MEC per feature, we have a quite low utilization rate. But this does not affect a lot the latency in this operation. But you can see that all over the entire network, we have a significantly high utilization rate, apart from the first layer. That means all the peripheral IP, like the analog digital converters, are used very homogeneously over the workload. And that means that we don't overuse any or underuse these individual blocks. In principle, we also have a high flexibility with this architecture. That means in principle, we can house various CNNs in this architecture, even if it's a fixed number of processing elements with a certain number of fixed memory, we can go over a very large range of networks which we implement on this. So that means the number of parameters stored is can be very different. It's still performing quite well because we do not have more periphery activated. So it only has an influence on the latency, or what we here use like frames per second. So the frames per second reduces with the size of the network. So if you have an extremely small network like LANet 5, we could theoretically have extremely high frames per second. But the higher the network, the larger the network, or the higher the network complexity gets, the frames per second reduce. But in principle, it's possible to map all these very wide neural networks on the same architecture. The only limitation we have is exactly the full amount of parameters to be stored. So for example, 1 megabyte, so or 8-bit 1 mega parameters, or a similar number. So that's the only limitation in this fully weight stationary architecture. But in principle, everything below can be flexibly mapped, and independent of those networks, we achieve the same energy efficiency and the same number of TOPS per watt. Now you would ask, the FeFET is a nice emerging memory device, but it's not yet mature. What is actually the influence of variation or mismatch on this operation? So here I showed you some experimental results of the VT variation dependent on the scaling of the FeFETs. So if we use a lab scale size maybe of 1000 times 1000 nanometer per FeFET, the VT variation is very small, but the smaller we get, so like 160 times 240, that's not even the smallest logic level MOSFET you could have in this technology node, but already you see significantly widened VT variation, which is a result of, for example, the grain structure of the ferroelectric layer in these FeFETs. And we can quite well simulate this with our compact model for the FeFET, which is using the same MOSFET compact model and adds a layer of the ferroelectric into this. And so using this simulation model, we can run a lot of such operations and see what the ADC output of this in-memory computing would be. Most of the time, even for the smallest, we don't see a change, but already a small portion of such operations where actually the result should be a 0, but we get a 1, can hurt the accuracy. This is actually less the case for all the variations for higher expected outputs. The ones which hurt are the ones where we would expect a 0, but we get the 1. Especially for these operations, we can do a 0 check. So if we would expect that the zeros should be a 0, but they are not because of the input, then we can say, okay, this has to still be a 0. That's what we call the 0 check. And the same, the ADC limit, if the maximum input is that number, the maximum result should not be higher than this input. So these checks can be implemented quite well. Here we simulated these configurations, having OR gates or single AND gates implemented. We simulated how this has influenced the accuracy. So we see that from a start, we have a floating point accuracy and go back to a quantized state like 8-bit input and 4-bit wait operation, still assuming that we have 4 individual FeFETs having a single level cell, 1 bit per FeFET scenario. Then normally this quantization does not affect strongly the accuracy. And this also does not change when we have these quite large FeFETs, 1000 times 1000 nanometer square. But it does when we go to smaller FeFETs. So for example, for VGG19, it drops from 70% to like 58%. But it is possible with these two limiting checks, very simple checks of the operation, we can go back to like almost 70%. So by adding these simple checks of operation, it is possible to go up back again to the software level accuracy, or in this case, maybe 3% of reduction. Yeah. Okay, good. And with this, I would conclude. We have seen the different memories which you can use in in-memory computing. I showed you ferroelectric field effect transistors. I showed you how we create compute macros out of this, and how this is then implemented in larger architectures using bitwise decomposition and a bit of algorithmic optimization to run in-memory computing with better accuracy. And with this, I would like to thank you very much for the kind attendance.
Great. Thank you very much, Thomas, for this great talk. Let me first stop the recording, and then we take